Hello, hello, hello. Another day working with functions is an exciting day. As we've seen, there are functions out there that do not happen to be linear functions, even though most of our year we have dealt with linear equations and linear functions. Okay, so for example, we've got our quadratic functions that we talked about last lesson. Those are the functions that are going to form some sort of parabola when we graph them. They're going to have a parabolic shape. We've also got the absolute value functions that we discovered during our lesson just yesterday. Those are the ones that when we graph them, they're going to form some sort of V. We can remember that because absolute value starts with a V. There are also cubic functions, which if we have time, we'll talk more about later. If you're interested, just Google it. For today, we're going to talk about exponential functions. Okay? An exponential function is an equation that has input values that are exponents. Basically, it's some sort of function that has an x, where our exponents would be. So, for example, you could have something as basic as y equals 3 to the x. You might have something as complex, or even more complex, as y equals s times 1 plus r raised to the n. That right there is a function that we use to model growth, like in a bank account, if we're going to make interest from year to year, if we leave money in the bank. And I'm sorry, I skipped one thing here. There are two types of exponential functions. The first type, the type that I've already shown here, we call exponential growth functions. You'll see in a second why it's called growth. But these types of functions are functions that have a whole number base. So for instance, right there, we've got our 3 as our base. Right here, once you determine what r is, you're going to have a number that is larger than 1. Okay, I'll show you what those look like in a second. Exponential decay functions might look something like this. Y equals 1/5 raised to the x. Or it might look a little more complex. It might look something like this. Oftentimes, exponential growth and exponential decay functions are used to model growth or decay in money that's in a bank account, or to model growth or decay of a population of animals, or a lot of times in science, you talk to Mr. Maurer and he'll tell you growth or decay of number of cells. If you guys have talked about half-life before, we often use exponential decay functions to represent the half-life in science class. So let's just jump right into an example here. Starting with an exponential growth function. It's graphed just the same way as we graph anything else. We need points that we can graph on our coordinate grid. So what do? We make our XY table. Just choose a couple points, and let's make it happen. If you plug in y equals 0.25 times 4 raised to the 0 power. Anything raised to the 0 power is 1 times 0.5. Therefore, this is going to give us 1/4. And let's plug the rest of these values in, and you'll end up with 1 and 4 and 16 and 64. So as we go over and graph, if you notice, our y values increased rather quickly after the first couple of numbers. Okay, and I'm not doing the best job of graphing these here because it should show a really dramatic increase in a second here. That's 3, 16, and 4, 64. There's our big jump. So if you notice, this is called an exponential growth function. Oh, Mr. Dudek, what are you doing? This is called an exponential growth function, and it's called that for a reason. If you look at its graph, I'm going to move this up a little bit for you. You'll see that as our x values increase, it looks like the graph is sloping upwards more and more as you follow the line. So it gets steeper and steeper the further we move to the right as our x values get larger. So very simply, you can say what's down here at the bottom of the paper. A function, like we've just graphed here, models exponential growth because we're growing as we move to the right. The slope is getting steeper and steeper. The graph will slope upwards as input values increase. So as our x values get larger, 1 to 2 to 3 to 4, our y values are going to get much, much, much larger, much, much, much quicker than if we were working with a linear function. Now let's flip this paper over and take a look at an exponential decay function. Let me get that on there for you so we can all see it. All right. So make a table with integer values of x from 0 to 5 for the function y equals 90 times 1/3 raised to the power of x. Then graph the function. Well, let's start our good old xy table. Let's put some values in here. And let's start plugging in. Y equals 90 times 1/3 to the 0 power, because I'm going to plug in 0 for x. Well, 1/3 to the 0 is just 1 times 90, and that's 90. Now take a second here. What do you think is going to happen when we plug in these larger values for x? What do you think is going to happen to our y values? In our other example, we saw what happened. The y values got larger and larger and larger very, very quickly. In this case, though, 1/3 to the first is just 1/3. Multiply it times 90, and you end up with 30. And all of a sudden, what's happening to our y values as we plug in our x values? This one's 1 1/10, and this one's about 0.37, or a little less than 4/10. You can check my math if you need to. Now let's go over and graph these values on our graph. There's my 0.90 and my 1/30 and my 2/10. And you should be realizing that, holy cow, this graph is way different than the one we just did that was an exponential growth function. As a matter of fact, it's almost the complete opposite. The graph more looks like it's falling now. Okay? That's why it's called an exponential decay function, as our x values, or our input values, are plugged into our function. Our value for y, or our output value, gets smaller and smaller and smaller, and it happens very quickly, okay, after the first or second value. That's why it's called exponential decay. So if you come to the bottom here, it says a function like what we have there, models, and you probably already know, is exponential decay. And the graph will slope downwards as the input values increase. Just in case you're forgetting here, we should really always put our arrows on the end of our functions, because remember, these are going to continue on in both directions. You can still plug in negative numbers, and you can still plug in bigger numbers larger than 5. And if you notice, this line right here, it looks like it's almost going to just go straight on the x-axis and be a completely horizontal line, but technically it's going to get ever so slightly closer to that line, but it'll never really be completely flat. If you keep putting more and more numbers, you'll just get a really, really, really tiny number. Okay, if you could answer these two questions at the bottom here for tomorrow, we'll be good to go. Have a great night.